Jai Hind, welcome to class of Analog and Digital Communication. We're going to talk about Unit 5, where we'll talk about time division multiplexing, TDM. Before we start with TDM, we need to understand what actually multiplexing is. So multiplexing, it is the process of combining multiple signals into one signal. Let's take example of a simple road where various trucks, buses, cars do travel. Let us suppose on a single route, on a single track, there is just one vehicle which is passing, and we allow those vehicles to pass one by one. Whereas if we compare the capacity of that road, that it can accommodate 3 vehicles at a time, and we want to utilize the efficiency of that road to its maximum, then what would we do? We would allow 3 vehicles at a time. Right? Same applies to the concept of multiplexing in case of communication. I do have a channel that has certain capacity, but because of some constraints, I am not using it to maximum extent. So what I can do is I can allow multiple signals to pass via that available channel in order to increase the efficiency of my system, right? So being electronics and communication engineer, most of us might have come across the term mux and demux, multiplexes and demultiplexes. Multiplexes are used at transmitter end, where we can simply combine various message signals to pass via a single available channel, and at the receiver side I may use a demultiplexer which would like segregate these signals again and pass it on to the intended recipients, right? So this is how my multiplexing and demultiplexing occurs. If the signals that I combine, those are analog in nature, then that kind of multiplexing is called as analog multiplexing. Whereas if I am combining the digital signals, then it is called as digital multiplexing, right? So here categorization is provided on the basis of what kind of input signals we do use. Now we might have heard one more concept of multiple access. I would like to clarify it here that multiplexing and multiple access both are similar thing, but we use the term multiple access in case of that kind of communication where my signals which are used at multiplexer are geographically separated, like in case of satellite communication, right? So multiplexing and multiple access are one and the same thing, but we do it specifically use the term multiple access for satellite communication where my users are geographically separate. Multiplexing was first developed for telephony. A number of signals were combined to send through a single cable. True. Now the process of multiplexing divides a communication channel into several number of logical channels, allotting each one for a different message signal or a data stream to be transferred. The device that does multiplexing can be called as mux, and the reverse process, that is extracting the number of channels from one, which is done at the receiver, is called as demultiplexing, right? The device which does that is called as demux. The device that performs multiplexing is called as multiplexer, and the device that performs demultiplexing is called as demultiplexer. What is the need of multiplexing? Here we can see in this diagram we are providing 31 inputs, and we are using a device which is called as mux here. It is combining these 31 inputs, passing it through one channel, one link, right? And at the receiver, the demux is segregating these again. What's the need? We know that channels are expensive. Just to clarify this point, being communication engineers, we know that two most important resources of a communication system are bandwidth and power. Being engineers, we must always design our system in a way that we require minimum power for transmission, and we to utilize the available bandwidth in most effective manner. So a good communication system will always require less transmission power and will always utilize the available bandwidth in its most efficient manner. So if we talk about the bandwidth portion, that is the most efficient utilization part, then multiplexing is the technique that solves the purpose. So that is the need of multiplexing. Transmission channels are expensive. It is often that two communicating entities do not fully utilize the capacity of the channel. For efficiency, capacity is shared. This is called as multiplexing. There are n inputs to a multiplexer. The multiplexer is connected by a single data link to a demultiplexer. The link is able to carry n separate channels of data. The mux combines data from n input lines and transmits over a higher capacity data link. The demux accepts the multiplex data stream and separates the data according to channel and delivers them to the appropriate output line. This picture represents how your mux and demux are connected. This is my mux, 1 to n input I may use, and at demultiplexing these are segregated. The primary uses in the field of communication, yes, of course. First of all, we used it for your telephoning, right? If I want to classify my multiplexing, then on the basis of type of message signal or input signal, I do classify it as analog or digital. If my input signals are analog in nature, that kind of multiplexing is called as analog multiplexing. If digital, then digital multiplexing. Then further classifying the analog multiplexers, we have frequency division and wavelength division multiplexing. And if I talk about digital kind of multiplexing, we have time division multiplexing. Although most of us do majorly know about TDM and FDM, that is time division and frequency division multiplexing. But yes, WDM is also a kind of analog multiplexing. And TDM can further be divided as synchronous and asynchronous. So here in our lecture, we'll specifically focus about TDM. Before that, I would like to give a brief overview of how my TDM and FDM are different from each other. So I've chosen a blank slide for it. We know the need of multiplexing, so that multiplexing is used to accommodate more number of input message signals to travel via single channel, right? So let's talk about analog signal, the classical kind of communication system. Here what we can do, let's suppose I am a standard body and I would be allocating some band to a particular vendor. We may talk about, let's take example of Jio or Airtel, considering these to be the biggest giants, and let's suppose that no other body exists. Then the complete radio band has to be which is prescribed for mobile communication, can be divided among these two giants, right? So let's take a simpler example. I do provide some allocation, some bandwidth to a vendor which I name as vendor A, right, and vendor B. If I allocate it to vendor A, and the band gap that I provide is, let's suppose, x to x plus 100, right? This complete band has to be then again be divided into the number of users that it sells its services to, right? So in case of frequency division multiplexing, on x-axis, if I consider there are various frequencies available, so I'll divide the frequency axis and in such a way. A pair of user will be provided with a fixed channel, right? And that would be of particular frequency, and no other user can perform communication in that frequency, right? So this is frequency division multiplexing, where my pair of users, they are allocated with a specific channel. Here, the advantage of such kind of system is no other user can communicate using this allocated frequency band. Whereas if I talk about the disadvantages, no two users to use the channel for 24/7, right? Let's suppose I use it for calling facility. I might use my uh, if A and B do like C and D to communicate in this channel, they will communicate for maybe a few minutes or few hours. So FDM is wasteful of bandwidth, and it is also wasteful of bandwidth. It is also a rigid system. More number of users cannot be accommodated. Whereas if I talk about TDM, when instead of frequency I divide the time domain, that many users can be communicating using the entire frequency bandwidth available in a prescribed time, and they too request for the communication they need to perform, and on request basis they are allocated band after particular duration of time. That would be called as time division multiplexing, right? It is somehow better than this. Reason, we can accommodate more number of customers, entire frequency band can be utilized by each user. And TDM exploits sampling theorem. How? We know that different signals are sampled at different frequencies. So if I see that samples have some time gap between their appearance, then in that time gap another samples from another signal can be accommodated, and this way we may utilize the available channel in a more efficient manner, right? So in TDM the time frame is divided into slots, and this technique is used to transmit a signal over single communication channel by allocating one slot for each message. Of all the types of TDM, the main ones are synchronous and asynchronous. In synchronous TDM, what happens? Input is connected to a frame. If there are n number of connections, then frame is divided into n time slots. One slot is allocated for each input line. Right? So in this technique, sampling rate is common. So one thing to remember, if we talk about synchronous TDM, sampling rate is common to all signals, and hence the same clock input is given. The mux allocates the same slot to each device at all times. If I talk about asynchronous TDM, here the sampling rate would be different for each of the signals, and a common clock is not required, right? So signals with different sampling rate can be accommodated in single channel. If the allotted device for a time slot transmits nothing and sits idle, then that slot is allocated to another device, which is an advantage, right? Unlike synchronous. Hence, this type of TDM is used in asynchronous transfer mode networks. So, in TDM, several connections share similar bandwidth. Here, multiple signals are carried, right? This way also I can show it. This mux, here I am showing it with the help of 3 input messages and demux to separate it. And signal, the actual information actually travel in the form of a frame, right? How it is accommodating different samples. Let me take an example. Let's suppose I'm using message 1 and message 2 and message 3. How my frame structure is formed? My first frame would be consisting of sample 1 of message 1, then sample 1 of message 2, and then sample 1 of message 3, preceded by sample 2 of message 1, sample 2 of message 2, and sample 2 of message 3. And likewise, although this would be the actual information and it would be padded with other bits like synchronization bits, handshaking bits, address of the transmitter, address of the receiver, the complete TDMA frame structure will not be simply the information, it will also be consisting of some redundant bits as well, right, which needs to be studied in detail. Now, if I talk about one of the prime example of time division multiplexing, this is T1 digital carrier system. Okay. Time division multiplexing, this is one of the prime example that one of the classical example of time division multiplexing. So, in order to understand this, we need to understand the concept of TDM in little detail. Like I have explained here that how my frame structure is formed, right? How these samples are taken and how are they forwarded. For understanding of this, we need to have a system that will be perfectly synchronized, isn't it? Let's suppose I am considering 3 message signals here. First of all, how sampling, how different rate of sampling is helping me in performing TTM. Let's suppose my message 1 was of frequency 5 kilohertz and my message 2 was of frequency 7 kilohertz and my message 3 was of frequency 10 kilohertz. Now, if we recall the concept of sampling, when we convert an analog signal into digital form, it has to follow sampling theorem. There are 3 steps for conversion of an analog signal into digital, which is sampling, quantization and encoding. And what does sampling does? Sampling converts a continuous time, continuous amplitude signal into discrete time signal, right? And it has to follow sampling theorem. Sampling theorem says that minimum number that number of samples that should be made in a second must be greater than equal to twice the maximum frequency content of the message signal. That is sampling frequency, fs must be greater than equals to twice of fm. This is what we need to follow. If I consider my first message, which is of 5 kilohertz, minimum number of samples that I have to make in a second must be 10,000, isn't it? If we talk about the second message, minimum number of samples that I have to make is at least 14,000. And if I calculate the time gap between the appearance of samples, that would be inverse of frequency. That is, samples are appearing after every 1 by 10,000, right? So, if my samples are appearing with some time gap, why not use that time gap in accommodating samples from some other signal, isn't it? So, I can accommodate these samples in this time gap as well as these samples in the time gap, and hence time, being my important resource for the communication system, can be efficiently utilized in transmitting my signals using time division multiplexing. And how these samples will be arranged? These can be arranged in this form. Now, at transmitter, my frame structure must be formed like this. This requires the presence of a device that will, accurately accept these samples and concatenate these in a manner that there occurs no difference, no error. So that device is called as commutator, right? Whereas at demodulator or at receiver, I do need a device that will do the reverse of it, which is called as decommutator. And this commutator and decommutator, they must be perfectly synchronized, because this is all the game of time. If there is little deviation in time, we might lose some samples, we might lose our actual information content. right? So time synchronization is very much important in case of time division multiplexing, right? So frame structure and synchronization, all these can be studied in detail. Now, if I talk about one of the prime examples of time division multiplexing, this is T1 digital carrier system. This was the classical thing that was developed on the concept of TDM. T1 digital carrier system is a North American digital multiplexing standard since 1963. T1 stands for transmission 1 and specifies a digital carrier system using PCM encoded analog signal. PCM was initially used for telephony. So T1 was used for telephony. It was initially used for combining 24 voice channels to pass via single line. A T1 carrier system is time division multiplexing. Multiplexes PCM encoded samples from 24 voice channels for transmission over a single metallic wire pair. Right? We know that earlier telephony was over wired network. So T1 system initially combined 24 voice channels. 24 customers can be accommodated at once. Each voice band has bandwidth this. This is the frequency of, this is audio frequency. This is the frequency of voice signal. Audio frequency is 20 to 20k hertz, right? Whereas my voice signal varies from 300 hertz to 3000 kilohertz. This is how it looks like. I can combine 24 voice channels. It uses pulse code modulation. This is a technique for conversion of analog to digital signal, right? It works at 4 kilohertz. Then TDM is used to combine it, right? T1 line, this is the data rate. We are going to prove it how the data rate comes out to be 1.544 Mbps. It is sampled at 8000 samples per second using 8 bits per sample. How it occurs? Let's see. It consists of 24 voice channels. True. A codec or coded decoder samples the analog amplitude of 4000. Why do I consider 4000? Whereas voice signal varies up to 3000 hertz, but we take some guard band and we for our to avoid any kind of error, we consider it up to 4000 hertz, right? Each at 8000 samples per second or 125 microsecond sample. If I calculate the time gap for samples for 8000 samples per second, it comes out to be 125 microsecond per sample for each of the 24 channels, right? Each of the 24 channels gets in to insert 8 bits into the output stream and 7 bits for the data and 1 bit for, here it uses 8 bit, like each sample is converted into 8 bits, right? Actually it is converted into 7 bit, but 1 extra bit is used for signaling. My Nyquist theorem says that signal of bandwidth W can be completely captured by taking 2W, minimum 2W samples per second. So for a 4 kilohertz voice signal, all information can be recovered by sampling at 8000 samples per second. Now this is clear that if we are using 4000 hertz voice signal, how many samples do I have to make per second? Minimum 8000 samples, right? And when samples are converted into bits, how many, here in this PCM I am using 8 bit quantizer. Sampling faster isn't useful, but sampling slower than the Nyquist means that some changes in the signal will be missed. So that is called aliasing effect, which we avoid here by sampling at a rate much higher than Nyquist rate. So each T1 consists of 24 into 8, which makes 192 bits, and for every 1 bit we are using at every frame. So total 193 bits we are using per frame. There are 8000 frames generated per second, so that makes 8000 multiplied by 193 bits, that makes 1.544 Mbps. That is the data rate of my T1 carrier system. 193 bits per frame, and one frame there are 8000 frames per second, so there will be 1.544 megabits per second generated. So this is the data rate of my T1 carrier system. It is shown with the help of picture here. 193 bit frame, where each bit has this bit duration 125 microseconds. TDM allows multiple T1 carriers to be merged into higher order carriers. If we further combine 4 T1 channels, it will make T2 channel, data rate for which for it will be 6.312 Mbps. If we combine 7 T2 channels, it will be the data rate, we can further rise it up to 44.367 Mbps. And if we combine 6 T3 channels, then the data rate can be increased up to this much, right? So that depends. The classical system we have studied in detail, and we can further improve the data rate by multiplexing it to further levels. That's it for today. These are the references I have used. Thank you.